want to talk about the issue of the half-life, right? And once again, the half-life is the time on average for one half of a parent population to decay into daughter products. Right? Now, most individual isotopes have a specific half-life. So you can have multiple isotopes of the same element, such as uranium, for example, that have different isotopes and therefore different half-lives. So each individual isotope of any given atom is unique, right? Now, once again, this works because of large numbers. If you only had a few hundred atoms present in a sample, it would be very difficult to establish good averages. But because samples, once again, even small samples, usually contain thousands, tens of thousands, if not millions, of individual atoms, the statistics become much better at those sizes, right? Um, so, for example, let's talk about carbon 14. Okay? So, carbon 14, carbon has 6 protons, and carbon 14 has 14 nucleons. Therefore, it has 8 neutrons. And this is an unstable nucleus, right? This is unstable. And so carbon 14 decays via beta decay, okay, into nitrogen. Okay, so carbon 14 decays into nitrogen, um, and an electron, right? Now, carbon 14 has a half life of approximately 5,730 years. So, what this means is that if I have some parent population, after 5,730 years, I'll have half of that parent population left. And then after two of those, or 11,460 years, then I'll have a quarter left. All right? So let's see how this works. So even though I just said this works because of large numbers, let's use numbers that we can work with. And let's just use 10 to the 6th. Okay? So this is 1 million. Right? So this is just for the sake of example. And what I'm going to do is I'm going to plot time on the x-axis and number of parents on the y-axis. Now at time 0, when my sample starts, this is going to be 10 to the 6th, right? If I take this sample and I set it in the laboratory, after 5,370 years, and I'm gonna round that to 5,700, the sample will have dropped by half. Right? The sample will have dropped by half, down to Um, well, half of a million is 500,000. So this would be 5e⁵, right? And then after another 5,700 years, so this is going to be close to 11,500, it will have dropped from by half of this. And half of 500,000 is 200,000. So it will have dropped to 200,000. 250,000, technically. So 2.5e⁵. And then, after another half-life, after roughly 17,200 years, it will have dropped by half of this amount down here. And so what this does, this creates an exponential curve. Now my artwork's not going to be great here, so I'm actually going to see if I can erase that and make it a little bit better. Whoop. So this isn't a straight line, okay? This isn't a straight line. This is what we call an exponential decay curve, right? So we have an exponential decay curve, and this is where math kind of diverges from reality. Theoretically, this exponential decay curve, the math used to describe this function, never actually gets to zero. But of course, in real problems, it's possible for all of the parents to decay. So this is a fine point, but usually we're interested in the data when it's in kind of these regions anyway. We don't have to worry about the data when it gets down to these, you know, several half-lives. Now, there are some situations where you do have to worry about, you know, 6 or 7 half-lives down the road. But for our elementary purposes, we're not going to go there, right? All we want to do, and if I make this a little bit bigger, then the curve will stand out a little bit more. I'm going to try to make these increments as evenly spaced as possible. And if I start here, then at the first half-life, I'll have half. Second half-life, I'll have half of that. Third half-life, I'll have half of that. Fourth half-life, I'll have half of that. And you can see that this is not a straight line. If this were a straight line, I would not be describing the function all that well. So that's why this line is curved, okay? From a visual standpoint, I should say, that's why this line is curved. And then it'll flatten out, right? So that's what we mean by the half-life, right? And your textbook actually goes through an example, a calculation with some simulated dice of how to actually calculate this function, okay? You can, if you have raw data, you can plug this into a spreadsheet and you can fit the data with a function of the form y equals a times e to the negative bx. And a is your theoretical parent population at time 0. Right? So a would be the total amount that you start with. And then b is related to your half-life. Right? B is related to your half-life. So when you fit um, a function with um, this curve. Now B is not your half life. Okay, B is not your half life, but B is related to your half life. Right. Um, in fact, I'll go ahead and give you the formula. I wasn't going to, but I will. The half life, the amount of time it takes to reduce your population by half, this time right here, is equal to the natural log of 2 divided by that b constant. Okay? So that will give you your half life in whatever units of time this is being measured in, whether it's seconds, days, years. There are some radioactive substances that decay very, very, very quickly, whose half lives are on the order of maybe just a couple seconds. Some are much even shorter than that, all the way up to billions of years for uranium 238. So there's a wide range of time scales that radioactive processes happen over. And that's one reason why we like to use radioactive dating for different types of situations. Carbon dating is very useful, particularly for old biological specimens. Um, but it's not terribly useful for example, say, dating something that's only 30 years old. Um, Same thing with your uranium type materials. On the other hand, things like polonium 211 decay on the order of seconds. And so you have various substances, various systems that will decay over different time scales. All right? So we will talk to you next time.